All right, so let's do problem 316 here. And this is a problem that causes a lot of students a little bit of trouble because a lot of students don't know where to start with this problem. All right, so what we're looking for, we're given kind of two separate things going on here. So we're given the original configuration of these springs to be here, right, in this configuration. And then we add the mass of these two cylinders at the bottom, and its final position in equilibrium is hanging down like this. Okay, so what we need to find here to figure out the mass in these cylinders, all right, so what we're trying to find is the mass of the cylinder. So okay, and several things that we know that the force in a spring, right, is equal to the spring constant times the amount it stretches. All right, so this is the amount that it stretches. All right, so if we want to think of x being the final length of the spring minus the original length of the spring. So it's not the total length of the spring, it's how much it stretches here. And we're given that K here is 100 newtons per meter. So if we apply 100 newtons to this, it should stretch a meter. All right, and what we need to realize here, there are two triangles because we need to figure out the original length of the spring and the final length of the spring. So we can do that by drawing some triangles here. So let's try to draw a triangle here. And we know that this leg of the triangle is 2, and we know that the length of this triangle is 1.5. All right. And then we also have another triangle, a bigger triangle once it stretches here. So we have a bigger triangle, and we know that the sag here is 0.5 meters. So this distance S is 0.5 meters. So the long leg of this triangle is 2 meters. So we know that's 2. Okay, so let's start our analysis here. Let's start at the analysis by figuring out the original length and the final length. So in our original triangle, we have this equal to 1.5 and then this equal to 2, and then the hypotenuse here is the original length of the spring. All right. So by doing the Pythagorean theorem, 2 squared plus 1.5 squared is equal to the original length of the spring squared. So our original length comes out to be 2.5 meters. Right? And then in the stretch condition, we have this leg being 2, and then this leg still remains 2, and this is our length of our stretch position, L. All right, so to figure out L, we use the Pythagorean theorem again, 2 squared plus 2 squared equals L squared, which then L is equal to 2.8284 meters. All right. Now we can figure out the total stretch of the spring. the total stretch of the spring is L minus the original length, and that comes out to be 0.3284 meters. So the force in each spring then is equal to K times X. So that's 100 newtons per meter, right? Times 0.3284 meters. All right, and that force comes out to be 32.84 newtons. All right, so we're almost there. We've figured out the force in each of these springs here. And now we just need to draw a free body diagram so we can figure out the mass of the cylinders. So let's do that. So in the stretch position, we have the two cylinders attached like this. And we have the spring forces acting in the directions here. And we know that these are 32.84 newtons. Let me write that again. 32.84 newtons. And we have the weight of the cylinders acting downward here and here. Okay, so this is our free body diagram. And we know that this triangle here is in the stretch position is 2 and 2, all right? Because that's just what we drew up top. So let's take the sum of the forces in the y direction, since this is an equilibrium in the stretch position, and let's write out the equation here. So we have two total springs, and then we have the spring force, 32.84 newtons, but it's not the full 32.84 newtons acting in the y direction here. All right, so we need to do a component of that, which is 2, the vertical component, and we know that the hypotenuse is 2.8284, right? So we know the hypotenuse. So it's 2 divided by 2.8284. All right, and the downward forces, we have 2 times the weight of one cylinder, and that is equal to 0. And with this equation, we have one unknown, the weight of the cylinder, and one equation. This should be solvable. So rearranging this equation, we get the weight of the cylinder is equal to 23.221 newtons. But this problem is asking for the mass of the cylinder, and remember that the weight of the cylinder is nothing more than mass times the acceleration due to gravity, which is 9.81 meters per second squared. And we know 23.22 is the weight of the cylinder, and we can figure out the mass of the cylinder as being 2.37 kilograms. So that's the answer to problem 316.